Hi guys, this is the EdExcel AS level further maths paper covering the Further Mechanics 1 module, and it's from the June 2018 series. I think at this point it would be a good idea to just take a quick overall look of the examiner's report for this particular paper. The response to this paper was varied. One thing that was recognisable from the examiner's report was that students had a very thorough understanding of the topics. Many people gave clear and accurate answers, but some students were underprepared, often lacking in confidence with applying methods for certain questions, and that's probably because they had a lack of practice. People gave sometimes a very convincing response, however, they gave a very circuitous route. Okay, so that's a quick look at the paper overall. Question number 1. A small ball of mass 0.3 kilograms is released from rest from a point 3.6 meters above horizontal ground. The ball falls freely under gravity, hits the ground, and rebounds vertically upwards. In the first impact with the ground, the ball receives an impulse of magnitude 4.2 Newton seconds. The ball is modelled as a particle. For part A, we have to find the speed of the ball immediately after it hits the ground. So for part A, I think it will be a good idea to begin by sketching out this situation. So we've got the ball, it starts from rest, it comes down, it hits this ground, and then it bounces back up. So we've got this speed before it hits the ground. We'll label this in green, and that's going down over here. Okay, and then it bounces back up. We'll show that in orange, and we're finding this over here, the speed of the ball immediately after it hits the ground. Okay, now to do this we would have to use the Suvat equations to find the speed just before the impact. Okay, so the speed just before the impact, let's write this down. The speed just before the impact we can find what this is using v squared equals u squared plus 2as. Okay, so we've got v squared equals u squared. It starts from rest, so we have 0 squared, plus 2as, so we have 2 times by 9.8 times by 3.6. So v squared, you'd find this to be 70.56, and therefore v is equal to the square root of 70.56. Now here we have to be a bit careful. If we assume that upwards is positive, okay, let's just quickly illustrate this. So if we assume upwards is positive, then the speed just before the impact, that will be minus 8.4 meters per second. Okay, so we have 8.4 meters per second going down, hence we have this minus. And we were also told in the question that we have an impulse of magnitude 4.2 Newton seconds, and we should know that the impulse is equal to the change in momentum. Okay, so we've got the impulse 4.2, and this is equal to the change in momentum. So if we factorize out the mass, the 0.3, then if we assume that it goes back up with a speed of w, we have w minus 8.4. Okay, and if we divide through by 0.3, we have 14 on the left hand side, and on the right hand side we have w plus 8.4. Okay, and therefore you can find w to be 5.6 meters per second. Okay, so we have 5.6 meters per second going back up. Hopefully that makes sense so far. And now for part B, we have to find the kinetic energy lost by the ball as a result of the impact with the ground. Okay, part B. For part B, what we're finding over here is the kinetic energy lost, and the kinetic energy lost, you'd find that to equal 1/2 mv squared minus 1/2 mw squared, the initial minus the final. Okay, so we have 1/2 times by 0.3 times by 8.4 squared minus 1/2 times by 0.3 times by 5.6 squared. You'd find we get 5.88 joules. In terms of question 1, that required us to use the Suvat equations to find the speed of the ball on impact with the ground. Many people did that successfully, but there was a bit of a problem with knowing what the definition is for the impulse momentum relationship. Many people made sign errors, and one thing you notice I did was I defined which direction was positive first before anything else, and that sort of eliminated the idea, or that would have helped to reduce the probability of you getting a sign error. What else happened? There were a couple of students who took no account of the change in direction of the motion of the ball. So once it goes and hits the ground, it goes back up. We were told that in the question somewhere. What else was important? Students who obtained a speed of rebound greater than the speed of impact did not appear to be troubled by this. Okay, fair enough. In terms of part B, where we have to find the loss in kinetic energy, that was widely understood, but there were a minority of students who used an initial or zero or final speed of 0, which was incorrect. You have to think of it in terms of this. Okay, we're not thinking of it from here to here. We're thinking about once it reaches here and goes back up, if that makes sense. Okay. Question number 2. Figure 1 over here shows a ramp inclined at an angle of theta to the horizontal, where sine theta is equal to 2/7. A parcel of mass 4 kilograms is projected with a speed of 5 meters per second from a point A on the ramp. The parcel moves up a line of greatest slope of the ramp and first comes to instantaneous rest at the point B, where AB is equal to 2.5 meters. The particle is modelled as a particle. The parcel is modelled as a particle, and the total resistance to the motion of the parcel from non-gravitational forces is modelled as a constant force of magnitude R newtons. For part A, we have to use the work energy principle to show that R is equal to 8.8. Okay. So for this question, first of all, if we know that sine theta is equal to 2 over 7, then we can draw this triangle to find out what cos theta are and tan theta are, just in case we need it. Now, for this part of the question, we've got this diagram over here. The parcel starts at A, it ends up at B. And for us to show that R is equal to 8.8, we would have to use the work energy principle. So using the work energy principle, let's just write this down. Using the work energy principle, at the point A, we're losing kinetic energy because the particle comes to instantaneous rest at the point B. So with the work energy principle, at the point A, we lose kinetic energy, and then of course at the point B we gain potential energy, and to get to the point B we would have to do work to get there. Hopefully that makes sense. And of course we would have to do work. Essentially we've got some sort of non-gravitational forces. In other words, we've got some sort of friction taking us from A to B, and we have to do work against that friction. So the kinetic energy lost, we have 1/2 times by 4 times by 5 squared. That's the kinetic energy lost at the point A. And at the point B, we've gained potential energy. So we have 4g times by 2.5 sine theta. So that's the potential energy gained at the point B, and the work done, we have the force times by the distance travelled, so we have 2.5 R. Okay, so we know that sine theta is equal to 2 over 7, so we have 1/2 times by 4 times by 5 squared equals 4 times by 9.8 times by 2.5 times by 2 over 7 plus 2.5 R. So we have 50 equals 28 plus 2.5 R. And if we rearrange for R, you'd find R to equal 8.8. Okay. And now for part B, after coming to instantaneous rest at B, the parcel slides back down the ramp. The total resistance to the motion of the particle is modelled as a constant force of magnitude 8.8 newtons. We have to find the speed of the particle at the instant it returns to A. This is a fairly difficult question in my opinion, and I think it would help if we redraw the diagram. So having drawn the diagram, if we use F equals ma, we can use F equals ma to find the acceleration, and once we found the acceleration, to find the final speed at A, we can use v squared equals u squared plus 2as to find the final speed. So if we use F equals ma in this diagram, and notice it's at B and it's going to A, and we've got this resistance of R still. So using F equals ma, if we use F equals ma, we've got the forward force, that would be 4g sine theta, that's resolving parallel to the plane, and then we've got this resistance force 8.8, and this is equal to the mass 4 times by the acceleration a. So we've got 4g times by 2 over 7 minus 8.8, and this is equal to 4a. 4a, you'd find that to equal 2.4. Of course, the acceleration is equal to 0.6 meters per second squared. So using v squared equals u squared plus 2as, if we use this, we've got v squared equals u squared, so we have 0 squared, plus 2as, so we have 2 times by 0.6 times by s, that's 2.5. The reason we have v squared equals 0 squared over here is because we were told somewhere in the question that when it's at the point B, it's at instantaneous rest. So the velocity at B is equal to 0. So v squared, that's equal to 3. Of course, the velocity at the point A, that's equal to root 3 meters per second. Okay, which is 1.7 meters per second. Now for part C, we have to suggest 2 improvements that could be made to the model. So for part C, in the question so far, we've assumed that we have constant resistance. Instead, as an improvement, we could have resistance being proportional to speed. And the second improvement, in the question we modelled the parcel as a particle, so the improvement would be to not model the parcel as a particle. In terms of question 2, that required us to use the principle of work energy. Overall it was done pretty decently. Obviously you have to show, if you show everything step by step, that would have helped in finding the final answer correctly. Relatively few students started their answer by writing down an equation for the change in energy and work done, like I did over here, and that, I think if you do that, that would help to sort of make sense of what's going on. In terms of part B, where we had to find the speed of the parcel at the instant it returns to A, you could use the approach of the work energy principle, but you don't have to do that. The change in direction of motion was not always taken into account, so there were several errors in sign. So I think over here I drew out a diagram again, and obviously the change in if you did use the work energy principle, gravitational potential energy was sometimes overlooked. The approach I took was F equals ma. That was quite popular. There were some sign errors with resistance to motion and the weight often acting in the same direction. Obviously R is not pointing this way, instead it's going this way. Many left their answer as root 3, which is inappropriate accuracy following a substitution for G. Yeah, that was my error. In terms of part C as well, part C, that was basically suggesting improvements to the model. Some students did not recognize the modeling within the question and had little understanding of how the model might affect the outcome. So I think somewhere in the question we were told in context what R was, that was a non-gravitational force, so that suggested friction. So a very popular suggestion was to consider friction, but this is already there in the total resistance. Okay, so bear that in mind. Very few students suggested that the parcel should not be modelled as a particle. I thought that was a very obvious response to give. Question number 3. A van of mass 750 kilograms is moving along a straight horizontal road. At the instant when the van is moving at v meters per second, The resistance to the motion of the van is modelled as a force of magnitude mu v newtons, where mu is a constant. The engine of the van is working at a constant rate of 18 kilowatts. At the instant when v equals 15, the acceleration of the van is 0.6 meters per second squared. We have to show that mu is equal to 50. I think it would be a good idea to begin by drawing out a diagram to illustrate the situation. So here you'd find our van. The van, of course, has a mass of 750 kilograms. We've got this driving force moving us forward, and we've got this variable resistance, which is equal to mu v. And we can first of all find out what this driving force is by using power equals the product of the driving force and the velocity. And we know that when v equals 15, we've got the power being 18 kilowatts. So using P equals Fd times by V, we've got 18,000 equals Fd times by 15. Of course, Fd, you'd find this to be 1200 newtons. And if we use the equation of motion, the sum of the forces is equal to the mass multiplied by the acceleration, we've got the forward force, Fd, the resistance force, mu v, and this is equal to the mass, 750, times by the acceleration a. And we know that a is equal to 0.6, we were told that in the question, and that's when v equals 15. So we have 1200 minus mu times by 15, so we have 15 mu instead. Let's just write that. And this is equal to 750 times by 0.6. We wish to solve for mu, so we have 1200 minus 15 lambda, equals 450. So we have 15 lambda equals 750. Of course, in conclusion, lambda is equal to 50. Now for part B, the van moves up a straight horizontal the van moves up a straight road inclined at an angle to the horizontal, where sine alpha is equal to 1 over 15. At the instant when the van is moving at v meters per second, the resistance to the motion of the van from non-gravitational forces is modelled as a constant force of magnitude 50 v newtons. When the engine of the van is working at a constant rate of 12 kilowatts, the van is moving at a constant speed, v meters per second. We have to find the value of v. Okay. To begin with, we need to draw out the situation. Having drawn this using P equals Fd times by v, hopefully you can therefore see from here that we have a power of 12,000, and this is equal to Fd multiplied by big V. Fd, of course, is equal to 12,000 over V. Okay, and if we use the sum of the forces equals the mass times by the acceleration, just as we did before, then what we have over here then is, if we go back to the diagram, we have Ft, the forward force, minus the 50V, and then we've also got this 750G sine alpha to take into account, and that's equal to the mass times by the acceleration. Now the acceleration would be 0. The reason it's 0 is because we were told that the van is moving at a constant speed, so therefore A is equal to 0. So we have 12,000 over V minus 50V minus 750G times by 1 over 15, and that's equal to 0. So tidying this up a bit, we have 12,000 over V minus 50V minus 490 equals 0. If we multiply through by V, then you'd find we have 12,000 minus 50V squared minus 490V equals 0. And if we divide by minus 10, we have 5V squared plus 49V minus 1200 equals 0. And now we just have to solve this quadratic equation. So V equals minus 49 plus minus 49 squared minus 4 times by A times by C, and then we square root this, and then we divide by 2A. So the two possible values of V, if you substitute all this into your calculator, we have 11.3 etc. and minus 21.1 etc. And therefore, because V must be greater than 0, because we can't have a negative power, you'd therefore find V equals 11.3 meters per second. Okay. In terms of question 3 for part A, people understood the work power principle pretty well. Many people did reach the final correct answer despite not forming an equation of motion at the start of their solution. I don't know if that made a difference or not. Part B, that was also done pretty well, but the only thing is, because the van was inclined at an angle of theta, you had to consider the weight of the van, and eventually you should be able to reach out some sort of a quadratic in terms of V. Some people did not reach that quadratic, and that was because of mistakes in algebra. And a positive and a negative solution. Some people did not reject the negative value of V being incorrect, and I think I talked about why V needs to be positive, because we need positive power. Question number 4. We've got this particle P of mass 3m, and it's moving in a straight line on a smooth horizontal floor. A particle Q of mass 5m is moving in the opposite direction to P along the same straight line. The particles collide directly. Immediately before the collision, the speed of P is 2u and the speed of Q is u. The coefficient of restitution between P and Q is e. We have to show that the speed of Q immediately after the collision is u over 8, lots of 9e plus 1. I think it would help if we draw out some sort of a diagram to illustrate what's going on. So I've drawn this diagram. We've got P and Q before the collision, and after the collision we've got speeds shown here as well. Now we want to show the speed of Q after the collision. The first thing we can do is use conservation of linear momentum, let's write this down. If we use conservation of linear momentum, we have 3m multiplied by 2u, and then we have minus because we've got q which moves towards the left, so we have 5m multiplied by u, and this is equal to 3m multiplied by v plus 5m multiplied by w. And just to emphasize this point, this is the situation before the collision, and this is the situation after the collision. And if we simplify all this, hopefully 6mu minus 5mu, that's just u, and here we have 3mv plus 5mw. Hopefully you can see why that's the case. And if we also use Newton's law of restitution, let's just write this down. Using Newton's law of restitution, E is equal to the speed of separation. Okay. And then we divide that by the speed of approach. Okay. So with that, we've got the speed of separation, that would be w minus v, and the speed of approach, you'd find that to be 2u plus u, because they're moving towards each other. So we have w plus v divided by 3u. And with this, we can rearrange this equation to say that w minus v is equal to 3eu. We'll call this equation 2. And if you go back to the question, in the question there's no w. So we need to solve equation 1 and 2 simultaneously to eliminate w. Okay? Well, first of all, from here, if we simplify this instead, hopefully, there's no m over here. So if we solve equation 1 and 2 simultaneously, hopefully we should be able to eliminate w. Okay, let's just write that down. We want to eliminate w from equation 1 and 2. So if we take a look at equation 2, we want to solve 1 and 2 simultaneously rather. So we want to solve 1 and 2 simultaneously rather. And if you look at equation 2, if we multiply that by 3, then we can add equation 1, 2, 3 together. So from equation 2, if we multiply that by 3, we have 3w minus 3v equals 9 EU. Call this equation 3. And if we add equation 1 to equation 3, adding them together, we have 3w plus 5w, that's 8w. And then the minus 3v and the positive 3v cancel, and on the other side we have u plus 9u e, or eu, doesn't make a difference. So if we factorize out a u from both sides, we have u lots of 9e plus 1. Okay, So 8w is equal to u lots of 9e plus 1, and therefore you'd find w to equal u over 8. If we neaten this up, we have u over 8 lots of 9e plus 1. We'll call this equation 4. Okay, and I think that's all we wanted to show. Yeah. For part B, we have to find the range of values for E for which the direction of motion of P is not changed as a result of the collision. Well, if the direction is not changed, of course V will be greater than 0. But before anything, we need to actually find out what V is, and we can do that by substituting equation 4 into a rearranged form of equation 2. Well, for part B, hopefully you can see that from equation 2, V is equal to W minus 3 EU, and if we substitute in for W, V is equal to U over 8 lots of 9E plus 1 minus 3 EU. Okay, and we need to expand and simplify all this. So we have V equals 9U over 8, 9U over 9 EU over 8. Okay, let's just tidy this up. And then we have an 1/8 of U minus 3 EU. So V is equal to U over 8 minus 15 over 8 EU. And if we factorize out a U over 8, hopefully you can see that V is equal to U over 8 lots of 1 minus 15 E. Okay, and using that condition of V being greater than 0, if we use this condition, we have U over 8 lots of 1 minus 15 E being greater than 0, and therefore you'd see that 15E is less than 1, and therefore E is less than 1 over 15. And one of the conditions we know for E is that E must be greater or equal to 0, and therefore the range of values for E, we have E which is greater or equal to 0 but less than 1 over 15. Okay, and now for part C. When P and Q collide, they are at a distance d from a smooth fixed vertical wall which is perpendicular to their direction of motion. After the collision with P, particle Q collides directly with the wall and rebounds, so that there is a second collision between P and Q. This second collision takes place at a distance x from the wall. Given that E is equal to 1 over 18 and the coefficient of restitution between Q and the wall is 1/3, we have to find x in terms of d. I think this question is actually quite difficult. So to do this, I think it will be a good idea to, first of all, if we know that E is equal to 1 over 18, we can use that to find V and W. Okay, so let's do that. We know what V is, we know what W is, so using equation 4 and equation 5, we'll call this equation 5. Given that E is equal to 1/3. We can use this to find out what V is. So V is equal to U over 8 lots of 1 minus 15 times by 1/3. V is equal to U over 48. And W is equal to, if we use our equation for W over here, W is equal to U over 8 lots of E is equal to 1 over 18 rather. So we have 15 times by 1 over 18, which is U over 48, and 9 times by 9 times by 1 over 18 plus 1. Okay, so you'd find W to equal 3U over 16. Okay, so now that we know V and W, I think at this point it will be a good idea to draw a quick diagram. So using the information we've got in the question, what do we know? When P and Q collide, they are a distance d from the wall. So when they first collide, they are at a distance of d from the wall, and then obviously once they collide, Q goes to the wall, and then this thing over here, technically speaking, I've drawn this incorrectly. This should be over here somewhere. Okay, we've not been told that P moves or anything, so Q goes to the wall, and then after that they go and collide again together. Okay, so I think that's a bit difficult to understand. So after the collision, P moves towards the right, and Q obviously goes back after it bounces from the wall, and they collide like this. Hopefully that makes sense what's going on. And we wish to find X in terms of D essentially. Now the first thing we can do is we can find out how long it will take Q to essentially get to the second collision. Okay, and the way to think about this is we have to think about the various different speeds involved. The way to think about this is to before anything, we need to find out what this speed y is when they bounce back. And we were also told somewhere in the question that the coefficient of restitution between Q and the wall is a third, so we can use that to find out what y is essentially. And the way we can do that is to use Newton's law of restitution again. So we've got the speed of separation, that's y, and the speed of approach, that's w. Okay, hopefully all that makes sense. So we've got w over here, and therefore we can set this equal to 1/3. We were told that in the question. So if we rearrange for y is equal to 1/3 w. We know what w is already, we worked that out over here somewhere, that's 3u over 16. So we have 1/3 times by 3u over 16, we get u over 16. So therefore we have y, which is equal to, if we move this a bit over here, we have y which is equal to u over 16. Okay, hopefully that makes sense. And what else we can do with that is we can now find essentially the time it takes q to get to this second collision. We can also do a similar thing with p, and we can therefore set those times equal to each other because they'll be at the same place at the same time, if that makes sense. So let's do that. The time to get to q, well, before we do that we have to write down a formula. Time is equal to distance over speed, and therefore the time for q to get to the second collision, so time for q to get to the second collision, this is equal to well, we've got the distance d over this 3u over 16. Okay, so we've got d over 3u over 16, and then we've also got this x over the u over 16 coming back as well. Okay, so we've got x over u over 16. Okay, so if we tidy this up a bit, we've got 16d over 3u plus 16x over u, and if we write these over a common denominator of 3u, you'd find we get 16d plus 48x. Okay, so that's the time it takes for q to get to the second collision, and we can do the exact same thing to find the time it takes us to get to, we can do a similar thing to find the time it takes p to get to the second collision. And you have to be a bit careful over here. The distance would be d minus x, and hopefully you can see why that is to get over here. And the speed at which it's going there is u over 48. So this time is equal to d minus x, that's the distance, over u minus 48. So we have 48 lots of d minus x over u. Okay, and the next thing to do is recognize that they'll be both at the same place at the same time. So we set these times equal to each other. So we have over here the 16d plus 48x over 3u, and we set that equal to this 48 lots of d minus x over u. And if we multiply through, if on the right hand side, if we change this to a 3u on the denominator, then on the top we'd have 144 d minus 144x. So hopefully this bit is the same as this bit, that bit. You should recognize that these two are equal. So we have 16d plus 48x over 3u is equal to 144d minus 144x over 3u. So we have 16d plus 48x equals 144d minus 144x. And if we tidy this up, we get 192x equals 128d, from which hopefully you can recognize x is equal to 2d over 3. And that's it. Question 4 was a bit difficult, but in terms of part A, that was done pretty well, because that was in the old spec. So if you recognize questions from the old spec, that should have helped you. If you drew a diagram, also that would have helped in figuring out the direction in which the particles move in. A small minority of students showed insufficient working to confirm that they had reached the answer given correctly. Okay, part B, this was like a question from the old paper. It was a little surprising to see several students thinking that the direction of motion of P depended on its speed relative to Q. A lot of students set up a correct inequality but gave an incorrect final answer due to incorrect work with the inequality and negative values. So I think part B, it was something 0 because the direction of P is not changed. In terms of part C, that was pretty hard. Some people, well, a couple of people completely misunderstood what they needed to do and forming equations because they completely misunderstood. Again, I think a diagram would help. Many people found the correct expression for finding the speed of Q, so I thought this y over here, but they failed to think what was happening. This was not helped by having particles moving in the wrong direction and misuse of the relationship between speed, distance and time, which are all over here.